Okay, our first problem is going to be a problem which uses Taylor polynomials, error bounds, and Taylor series. So what we want to do is we want to use Taylor's inequality and to find the right degree n polynomial to approximate this function g of x with a certain amount of accuracy on some interval. And then we're going to have to write it out. So whenever you don't have an n, it's always going to be one start, and we're always going to start with using Taylor's inequality. So let's write this out. So Taylor's inequality says that g of x minus Tn of x, where Tn of x is the nth degree Taylor polynomial, well, that is less than or equal to m over n plus 1 factorial times x minus x0 to the n plus 1. We heard x0 is equal to 0, so this is 0. And what is m? Well, m is the maximum on our interval I of the n plus first derivative of x. Sorry, we're using g here. Of g. Okay, so what is I? Well, I is the interval given. I is the interval 0 to 0.1. Okay, so and our goal here is going to be to find n. Right, this is our bound. This right here is our bound. We're going to have to somehow compare it with our accuracy, with our desired accuracy. Okay, the other thing is that whenever you do this sort of thing, we're going to have to find a pattern for the derivatives, because we need, we need this for arbitrary n. We're going to have to be able to write this in terms of n, so as a variable in terms of n. Well, let's start this. Well, we have g of x is equal to, this is e to the minus 5x. So then g prime of x, which in this notation is g1 of x, right? Well, that's just minus 5 e to the minus 5x. And then we get g2, which is the second derivative. Well, this is minus 5 times minus 5 to the e to the minus 5x. Right? It just brings down another minus 5. So we get minus 5 squared e to the minus 5x. Let's do one more until we're sure we see the pattern. g3x, the third derivative, is minus 5 times minus 5 squared. It brings down another minus 5 e to the minus 5x, or minus 5 cubed e to the minus 5x. Okay, so I think we see the pattern. The pattern is that gn, the nth derivative of x, is going to be minus 5 to the n e to the minus 5x. Right? Okay, so I'm going to write, simplify this a little bit. We can write this as minus 1 times 5 to the n e to the minus 5x. And this is always a good idea. You always want to separate your minus 1. So by the properties of this, we can write this as minus 1 to the n 5n e to the minus 5x. Okay, so now we have gn. What we really want to do is find m. So to find m, we need the maximum on our interval of gn plus 1. So let's go to our next page. M is equal to the maximum, while our interval is 0 is less than or equal to x, less than or equal to 0.1, I believe. Yes. 0.1 gn plus 1. Well, that's going to be minus 1, absolute value minus 1 to the n plus 1, 5 to the n plus the n plus 1, e to the minus 5x, all in absolute value. Now, remember with absolute value, we can go ahead and do this, as in we can take the absolute value of each part and multiply, right? Now, absolute value minus 1 to the n plus 1, well, we'll just look at minus 1 to the n plus 1. Minus 1 to the n plus 1 is equal to, takes on two values. It's minus 1 for n even, right? Because when n is equal to 2, we have minus 1 to the 3, which is minus 1, and it's 1 for n odd. But in either case, absolute value of minus 1 to the n plus 1 is equal to 1. So that just comes out. Now, 5 to the n plus 1 is greater than 0, so absolute value of 5 to the n plus 1 is equal to 5 to the n plus 1. And then the same thing for the exponential. The exponential is always positive, so its absolute value is just e to the minus 5x. Okay, so what we have is that m is equal to the maximum value for x between 0 and 0.1 of 5 to the n plus 1 e to the minus 5x. Now, of course, this doesn't depend on x, right? So we can bring this outside. 5 to the n plus 1, maximum value e to the minus 5x. Now we want to think about this. So this comes up a lot, the maximum value of something like this exponential. Now, well, let's think about what does the exponential look like? A positive exponential does this, right? This is e to the x. Well, a negative exponential does the other way, right? This is e to the minus x. So e to the minus 5x is going to do the same sort of thing. It's going to have the same shape. In particular, it's e to the minus x minus 5x is decreasing. Always, right? It's always getting smaller. So what that means is that its maximum value is always going to be on the left endpoint. So here that left endpoint is x equals 0, the smallest x value. Therefore, max of e to the minus 5x is equal to e to the 0, which is 1. Okay, so what we have is that m is equal to 5 to the n plus 1. That's the maximum value always. So now what we know is that the error g of x minus Tn of x is less than or equal to 5 to the n plus 1 over n plus 1 factorial, and then we had x to the n plus 1. Now this is a bound that holds for every value of x we choose. Any value of x, this works. But we want the maximum error, right? We want to say it estimates it within some accuracy like this, so we want the maximum error to be less than 0.01. So what we now want is the maximum of 5 to the n plus 1 on the same interval I over n plus 1 factorial x to the n plus 1. Well, this is going to be, of course, these guys don't depend on x, right? So they can come back out. Don't depend on the interval. So we have 5 to the n plus 1 over n plus 1 factorial. Maximum of this interval. Now x is increasing, right? So this is my picture of x. X to the n plus 1, that's x, right? So this is increasing. So we're always going to have to choose. The maximum is always going to be on the right endpoints. So the largest x value. Now the largest x value here is 0.1 or 1/10. So I'm just going to go ahead and write that in. I'm going to write that minus Tn of x. Well, we had 5 to the n plus 1 over n plus 1 factorial. And now I have 1/10 to the n plus 1. Okay, now we want this error. This is our max error. Now the claim is that we want our max error to be equal to 0.01. So let's just go ahead and solve for n now, right? We're trying to find the right n values. To the n plus 1. Well, I could simplify this a little bit, so I can bring this 5 in here, right? So I have 5 over 10, which is just 1/2. So I have 1/2 to the n plus 1 over 1 over n plus 1 factorial. Okay, so now we want to set this equal to 0.01, or 1 over 100. Okay, so it's going to be hard to choose the right n value. So what we're going to do is we're just going to test. I'm going to call my left-hand side equal to 1 over 2 to the n plus 1, 1 over n plus 1 factorial. Okay, so when n equals, and we're starting at n, let's just see, when n equals 2, left-hand side, we just plug this in, and we get 1 over 48. Well, this is greater than 1 over 100, so can't use that. We want something smaller, right? N equals 3. Left-hand side is equal to 1 over 384. Oh, okay, so this is less than 1 over 100. So n equals 3 gives, well, the error is f of x minus t3 of x. Well, we know it's less than or equal to 1 over 384, which is less than 1 over 100. So, in fact, we have that f of x minus t3 of x is less than 1 over 100. Okay, so t3 is the one we want. Now, I think it also wants us write the degree n Taylor polynomial in summation notation. So, we can also write this out now that we know what Tn looks like. Now that we know the derivatives look like, we can say Tn of x is equal to the sum, n equals 0, or sorry, the sum, j equals 0 to n of some terms aj, xj, right? That's just the definition for that. Now aj, we found these, right? aj Well, that's just the derivatives, right? This is aj. This one's a1. And we just plug in at the point that we want, at 0. So aj is equal to gj, the jth derivative, at the point 0, because this is our base point. And then it's all over j factorial. Okay, we already found these. So what we have is that Tn of x is equal to the sum j equals 0 to n. Well, when we plug in 0 for any of these, we just get 1, right? So what we have, minus 1 to the j, right? Is that what we found? Yep. We have minus 1 to the j, and then 5 to the j, and we plug in x equals 0, and we're just going to get 1 here. So minus 1 to the j times 5 to the j over j factorial, and then we need our x to the j. Okay, so that's our Taylor series, or nth degree Taylor polynomial. Now it wants one more thing. This problem is so long, and it says write the Taylor series for g of x. Now, the Taylor series is just the limit as n goes to infinity of the Taylor polynomial. So we say this is equal to the limit as n goes to infinity of Tn of x. Well, that's just making the upper bound of this sum infinity. J equals 0 to infinity. None of the stuff inside changes. Minus 1 to the j, 5 to the j over j factorial, x to the j. So this is also our Taylor series in summation notation, and we are done.